Right. So, we are talking about the two security portfolio with a risk free asset. In that case, as I mentioned earlier, we arrive at the conclusion that maximization of this particular ratio, which is called the Sharpe ratio, enables us to achieve optimality for particular set of securities. Now, we will briefly explore the 3 security case, because it is symptomatic of the generalization of the number of securities to, because in the actual market there are a huge number of securities in existence. So, 2 securities is a slightly simplified version, a toy version. It is more useful, it is more instructive to understand the 3 security case, because this can be directly generalized to n number of securities. An example of 3 securities case is on the left hand side of the screen. On the right hand side of the screen, let me explain this diagram. Let us say we have got A, B and C. Now, we have got 3 securities. So, the number of equations that we have in this case is 1 for sigma p in terms of sigma p square having a extended expression. Then we have an expression for R p, that is 2. We have x 1 plus x 2 plus x 3 equal to 1. We have 3 equations, and we have x 1, x 2 and x 3 as our degrees of freedom. Now, because of the 3 equations, we can eliminate 2 of the x's. Let us say we eliminate x 1 and x 2. So, what are we left with? We are left with, after eliminating x 1 and x 2, we are left with sigma p, let us call it x, R p, expected return. I am writing it for brevity, I am not using the ERP, you can use R bar if you like, which is y, and then we are having x 3 which is equal to z. These 3 variables are to be determined. Now, if you using this set of values, if you eliminate x 1 and x 2 out of these and use this notation, this is the expression that you arrive at, x square minus 3 by 4 y square. This is what you get by eliminating x 1 and x 2 from the set of equations, where x is sigma p, y is expected return and z is the composition of x 3. Now, it is clearly seen that for any value of x 3, now this is important, for any value of x 3 we get a hyperbola. Whatever value x 3 takes, let us say we externally we put a value of x 3 equal to say 0.2, we get a hyperbola. What does it mean? It means that for suppose this is my z axis, this is my z axis, this is x axis, this is y axis, this is the x 3 axis, that is z axis. That means what? That means for any value of z, let us say I pick out a value, let us say this is 0.2, and then I plot the risk return of the combination. That means I take x 3 equal to 0.2 and I plot the risk return of x 1 and x 2 in terms of sigma and r. I eliminate, you see x 1 and x 2 have already eliminated. So, I get a curve by putting a value of x 3 equal to 0.2, I get a curve between r and sigma. Now, that curve is a hyperbola like this. For x 3 equal to 0, I get a hyperbola. For any value of x 3 equal to 0.1, I get another hyperbola. For x 3 equal to 0.9, I get another hyperbola. So, what I am getting is, I am getting a hyperbola on planes which are parallel to the xy plane, corresponding to different values of these z coordinate. Different values of z coordinate have a plane parallel to the xy plane, and on that plane you get a hyperbola. This is what the portfolio possibilities region looks like. If you have I briefly reiterate what I am saying. For any you pick out a value of x3 and you will find that when you plot that value of x3 and you plot the set of values of x and y, that is sigma p and rp, you get a hyperbola. In other words, what happens? You have a plane corresponding to the value of x3 which is parallel to the plane of this board. This is the xy plane, so that plane would be parallel to this board, and on that plane you will get a hyperbola. For another value you will get another plane, on that you will get a hyperbola. These hyperbolas need not necessarily at all be parallel in terms of their orientation. They can be oriented differently, that is a separate issue, but they will be hyperbola, that is for sure. Okay. So how do we do the optimization now? Now our optimization has to be two pronged. Number one, we have to select that hyperbola out of this family. This is a family of hyperbola. For every x3 I get a hyperbola. So this entire family of hyperbolas, I have to select that hyperbola such that my risk free rate, that from my risk free rate, if I draw a tangent to that hyperbola like this point, this f corresponds to this f, and from here if I draw a tangent along this, then this particular tangent should have the maximum slope. For every hyperbola I will have a tangent. This is one tangent, this is one tangent. Similarly, there will be a hyperbola here that will have a tangent. I have to identify that hyperbola for which this tangent has the maximum slope. That is step 1. Identify that hyperbola for which the tangent from the RF point gives us the maximum slope. And secondly, once you identify that hyperbola such that this tangent is having the maximum slope, obtain the coordinates of the point of contact of that tangent, the tangent with the maximum slope, and that particular hyperbola. Let us say we index our hyperbolas by a continuous index alpha. All these hyperbolas are indexed by alpha, where alpha is this coordinate. Let us say we do that, and we, for a particular value of x3 equal to k, I get a hyperbola such that my tangent from the RF, from this RF, that is this point has the maximum slope. Then I need to find the coordinates of p dash. Once I know the coordinates of p dash, I know the composition of the securities that form this particular point, because I know x3 and I know the I know this point p dash, the coordinates of this point p dash. So I can find out the remaining securities. This is the geometric interpretation of the optimization, this geometric backdrop of the optimization process. What is the mathematics? And this is the mathematics. If you look at this is what the Sharpe ratio is. Tan theta is equal to, this is Rp minus Rf, Xi Ri is Rp, summation Xi Ri is Rp minus Rf divided by this expression is sigma p. So we are maximizing Z, or any value you can, any name you can put here. Tan theta is equal to Rp minus Rf upon sigma p, and this is nothing but the Sharpe ratio. So we want to maximize this expression. The maximization, how it is done? Now here the degrees of freedom are what? The degrees of freedom are the composition of the securities in the portfolio, x1, x2, x3, x3 which go into the portfolio P, xi, x1, x2, x3, whatever they are, they go and form the portfolio Rp. In fact, you can write this Rp as sigma xi Ri, which is done, which is what it is here, and you can also write sigma p as the standard deviation of the portfolio using the constituents. On simplification, taking the derivative partial derivatives with respect to each of these xi's, because we are optimizing with respect to each of these xi's, and we end up on simplification we get these optimization equations. So, if we can solve these optimization equations, we arrive at the optimal portfolio corresponding to a given risk free rate. Please note, this particular exercise assumes the existence of a risk free rate, and therefore, the optimal what is the efficient frontier now? Let us go back for a minute. This represents this f dash, let us call it f dash p dash represents the efficient frontier, provided of course, this is the best, this is the maximum slope hyperbola, and this p dash is the point of contact of the hyperbola and this particular tangent, then f dash p dash represents the efficient frontier. Please note in this context that we are assuming here that there is a risk free rate R f embedded in the problem which is given to us. So, what are the, this is where in fact Markowitz leaves us. Let us recollect what are the fundamental assumptions here. The assumptions were expected return is a function of risk, expected return is a function of risk, that was the first assumption, and the second thing was that particular risk, whatever this risk is measured by standard deviation. These were the two fundamental assumptions that went into the Markowitz analysis: expected return as a function of risk and risk measured by standard deviation. Now, we move from Markowitz to CAPM. Now, if you look at this, the entire Markowitz framework is focused on the investor side. How does the investor achieve the optimal portfolio, or how does the investor attain the efficient frontier from where he can select his optimal portfolio. So, that was what Markowitz was bothered about, that was what he was concerned about. Sharpe came about, and Sharpe looked at the whole situation from a slightly different perspective. He looked at the situation from the perspective of the market. He looked at it from the perception of the market. What he said was, okay, let us assume that all the investors in the market, do the optimization exercise as per the Markowitz mean variance optimization framework. Then, and if we require that at equilibrium, the supply and demand of every security must be equal. The supply must equal the demand for each security. Number 2, and this is number 2. Number 1, everybody does optimization as per Markowitz framework. Then, what is the pricing mechanism prevailing in the market? That was the question that he tried to answer. Of what, or how did the market price or determine expected return? What were the factors that went into the determination of expected return in this scenario? Which scenario? Number 1, Markowitz mean variance holds for all market players, all participants in the market, and number 2, supply equals to demand for all securities. So, we wanted to answer these questions. Number 1, whether standalone risk, which is measured by standard deviation, is an appropriate measure of risk from the market perspective, and number 2, does market price standalone risk? In other words, if somebody is taking a higher standalone risk, a higher standard deviation risk, will he get a higher expected return? Does market say, okay, because you are taking a higher standalone risk, you will get a higher return? Does market behave that way? That was the question he tried to answer, and whether market risk was in a sense related to the standalone risk, that was the second question. Let us try to understand why this question arises. Let us say we have two securities A and B. The standard deviation, which is a measure of standalone risk, standard deviation which is a measure of standalone risk is the same for both the securities, 6%. Standard deviation for A is also 6%, standard deviation for B is also 6%. And both the securities are priced in such a way that the expected returns are also 10%. So, both securities for the moment have the same standalone risk and therefore, and they are priced to the same return, which is 10%. Let the correlation between the two securities be 0.50. Now, what you do? You constitute a portfolio comprising of equal weights in money terms of A and B. Say you invest rupees 1000 or 1 million whatever, and you invest half of that in A, half of that in B. Because the expected return of a portfolio is the weighted average of the expected return of the constituent securities, it is very obvious that the return of the portfolio will also be 10%. The expected return of the portfolio will also be 10%. What about the return? What about the standalone risk? What about the risk? If risk were to be measured by standard deviation, then if we work out the variance and standard deviation as per this formula, we arrive at sigma p is equal to 5.2%. So, let me repeat, we have two securities A and B, both have the same risk in terms of standard deviation of 6% and both have the same expected return of 10%. I constitute a portfolio of A and B, the correlation between them is 0.50. I constitute a portfolio of A and B, equal composition of A and B, and I find that I end up with a new security. Portfolio is nothing but a point in risk return space as far as we are concerned. So, a security and portfolio for all practical purposes are the same. So, I constitute a portfolio or a security, a new security which has an expected return of 10%, but a standard deviation of 5.2%. Therefore, there is some problem somewhere with standard deviation being the appropriate measure of risk from the perspective of the market. That is what Sharpe tried to address. Now, let us go back. If we recall the Markowitz optimization mechanism formulation, Markowitz optimization was achieved by maximization of the Sharpe ratio. Maximization of the Sharpe ratio. When we reached a stage where the Sharpe ratio was maximum, we have said that the portfolio is the optimum portfolio. Now, if that is so, if that is the optimization criterion, then I would add a security to my portfolio. I will add a security to my portfolio provided the adding of that security to my portfolio increases or improves my Sharpe ratio. And I will continue to add securities to my portfolio until I continue to achieve this process of improvement. And when this process of improvement stops, I have achieved the best possible portfolio and it is the optimal portfolio. So, let us assume that I add a security, I have a security P, I add a security S to the portfolio P to have a new portfolio capital T. Let us see what is the condition under which my portfolio's Sharpe ratio would improve. In other words, what is the condition that the Sharpe ratio of T would be better than the Sharpe ratio of P. So, the return of T, the expected return of T would be the weighted average of the return of my existing portfolio plus the return of the added security, that is 1 plus 1 is the weight of my existing portfolio and x is the small addition that of S that I have made in one a unit of P to get T. So, this is the weighted average the return of the portfolio T, and this is what I get as far as the variance goes. Remember, the weights are 1:x. 1:x is the weights of P and S. Therefore, the variance or the standard deviation works out to this. When you take this 1 plus x which was within which was square within this. So, if you take it out, you get that square goes, and this is what remains within the squares. If you work to first order, you assume that x is small, this is small, then x square can be ignored. We are working to first order, so x square can be ignored, and we have this expression. Taking sigma p common, we end up with this. Now, taking sigma p common, we end up with actually 1 plus 2 rho x sigma s upon sigma p, but this 1 by 2, see what I have used is 1 plus x to the power 1 by 2 is approximately equal to 1 plus x by 2 to first order. We are ignoring x square. So, we are not considering higher order terms, and when I use this here, this 2 goes with this 1 by 2, and I am left with x rho sigma s upon sigma p, with this sigma p being taken common outside the brackets. The new Sharpe ratio, this is the Sharpe ratio, this is the Sharpe ratio, works out to this. Therefore, the new Sharpe ratio, for the new Sharpe ratio to be greater than the old Sharpe ratio, we require this condition. RS minus RF is greater than rho sigma, and this is nothing but, you will recall we have talked about this term many times earlier. This is nothing but beta S, and at equilibrium the two must be equal. Why? Because if either of the side is greater, if this is greater, I will keep on investing in this, and if the reverse equality holds, I will do shorting. I will take a short position in this, and again I can improve my portfolio. So, the net result is that at equilibrium the equality must hold. So, if this is greater than this, then I will invest in this, and if this is less than this, I will short this particular security, and again I will improve my Sharpe ratio. So, either way, if there is any greater than less than here, any imbalance here, this could result in a convergence. This could result in a convergence, and as a result equilibrium dictates that this may hold, and this is a very important equation. This leads us to the CAPM. Let us see how. We make some radical assumptions which are embedded in CAPM. We say that the inputs that go into the determination of the Sharpe ratio are the same for all the investors in the market. Now, if the inputs that go into the determination of Sharpe ratio are the same, everybody will determine the same highest Sharpe ratio, and therefore, the same highest portfolio Sharpe portfolio of risky assets. So, there will be homogeneity, and all players in the market, all investors in the market will have the same highest Sharpe ratio portfolio in the market. How they will determine their precise portfolio will depend on this line F, and let us say this line P, it will be a mixture of the risk free asset and that highest Sharpe ratio portfolio depending on the risk tolerance. Somebody may select it, somebody who is highly risk averse may select it here, somebody who is more risk taking may select here, somebody may even go beyond this by borrowing at the risk free rate and investing. Now, what happens if all investors, it is important. So, what are we saying? We are saying that all investors will hold combination of this is the risk free asset, and this is a particular portfolio which is the highest Sharpe ratio portfolio. Everybody is going to take some combination of this. Now, this portfolio comprises of the risky assets, and everybody uses this same portfolio for putting it in his portfolio as per his risk tolerance. This means what? This means that the cumulative securities that constitute these portfolios would be equal to the market outstandings of those securities. In other words, the proportion of the securities which form this portfolio must be the same as the proportion of the securities that are available in the market. Because every player in the market, see, every player in the market is using the same set of same proportion of the same securities. Let us take an example. Suppose there are two players in the market, A and B, and there are two securities X and Y. If A is let us say A is using two securities of A and X and 3 securities of Y, and B is using say 10 securities of X and 15 securities of Y, the market outstanding will be how much? The market outstanding will be 12 and 18, which will be in the same ratio as this or this. In other words, this and this will all be in the same ratio. Therefore, what we are trying to say is that this P ends up being nothing but the market portfolio. This P is nothing but the market portfolio. And not only that, this P is the market portfolio, and this is also the highest Sharpe ratio portfolio. So, the market portfolio happens to be the highest Sharpe ratio portfolio, and all investors will combine this market portfolio and this risk free asset as per their risk tolerance. So, what happens? Because this is the highest Sharpe ratio portfolio, its performance cannot be improved, any subsequent optimization cannot be done, and therefore we must have that for any security RS minus RF must be equal to beta S into RM. Now, here please note, I am not using RP, I am using RM. Why? Because we have now shown that RP is nothing but the market portfolio. So, this is nothing but the CAPM equation. Of course, we need to put a bar here, we need to put a bar here. So what did we have? We had RS bar is equal to RF plus beta S RM bar minus RF. Now, please note this bars means on the average. On the average, the expected or the return from a security S will be given by this expression. And this implies two things. This implies number one, that any spontaneous return, no, the important thing is this means on the average. Now, because we are talking about on the average, spontaneous returns can deviate from here, they will contain a random element. In other words, it is not that every return that is measured of a security S will satisfy this equation, it is not true. When returns are measured over a sustained period of time, then this condition may be met. However, when we have spontaneous returns to measured, they will contain an element, as we have been talking about, a random element, and this means that this is nothing but our good old regression equation. We have our regression equation in this form, slightly modified version. This gentleman here is nothing but the systematic risk, and this gentleman here is nothing but the unsystematic risk. So, another point here, the risk is partitioned into systematic and unsystematic risk. The return is partitioned into a component which is related to systematic risk, which is called risk premium. This is called risk premium. The part related to systematic risk is called risk premium, and the other part is a random component. And as we shall see very soon, this partitioning of the return into the systematic return and the random component also manifests itself as a partitioning of the risk into a systematic risk, this component, and the unsystematic risk, which is this component. So, systematic risk, unsystematic risk, this systematic risk is rewarded by the market by this particular risk premium, and the unsystematic risk continues to be random. So, let us summarize. Standalone risk is measured by standard deviation or variance, we have talked about it earlier, but standard deviation is not an appropriate measure of risk. Market does not price standalone risk, market does not price standard deviation risk. Beta is a measure of risk which is priced by the market. Beta is a risk which is priced by the market, and this pricing by the market of a risk is called systematic risk. So, the total risk of a portfolio can be segregated into two orthogonal components: the systematic risk, which is the beta risk, and the unsystematic risk, which is the random risk. Market does not price total risk, market prices systematic risk, market does not reward investors for unsystematic. Let us come back to it for a minute. Market does not price total risk. What does it mean? It means that suppose I have a portfolio that has a total risk of sigma p, and this particular total risk that I have has some component of systematic risk, let us say beta sigma m, and some unsystematic risk, let us call it sigma I. Now, sigma E I, let us call it. Okay. So, this is systematic risk, this is unsystematic risk, this is the total risk. Now, what we are simply trying to say here is, if I have a portfolio having this total risk, I can, retaining that same risk, improve the expected return if I cut down on this and I improve by if I improve the systematic risk or increase the systematic risk at the cost of unsystematic risk, I can improve the expected return. To repeat, if I have a fixed total risk, I can achieve an improvement in the portfolio performance on the average over a period of time, provided I eliminate that unsystematic risk, I take this to 0 and I compensate this by taking more of this. Conversely, if I want to keep the return fixed, I can reduce this by killing off this and thereby taking a lower level of total risk. Either way, the important thing is market will reward you with the beta risk, not with the sigma risk. We will continue from here. Thank you.